Hello everyone, my name is Zhang. Here I'd like to present our work, Rowhammering storage devices. The work has been done in collaboration with Boris Pismenny, my advisor Don Porter, Don Tsafrir, and Aviad Zuck. In this talk, we try to explore the feasibility of rowhammering the DRAM inside an SSD using just the standard storage command. The reason we do this is to try to understand whether the small embedded system within the device is vulnerable to the same rowhammer attack like a big system. To warm up, we start with some DRAM concept. The DRAM is organized with multiple hierarchies, including channels, DIMMs, ranks, and banks. Inside a single bank, the DRAM cells are organized in a two-dimensional array, which is addressable by row and column numbers. Each DRAM cell acts as the capacitor, which stores bits by the charge stators. And the cell will lose charge over time, which will lead to a data loss. So they need to be refreshed in intervals, commonly every 64 milliseconds, to restore the charge status. In a rowhammer attack, the attacker will try to accelerate the charge leak effect in order to induce disturbance error intentionally. To do this, the attacker picks an aggressor row, which is marked yellow in the figure, and repeatedly open and close the row at a high frequency. This will make the two adjacent rows, also called victim rows, to leak charge faster. When the charge leak is faster than the refresh rate, a bit flip may happen in one of the cells of the victim rows. This is how a common rowhammer attack works. And in our work, we will use a more effective variant called double-sided rowhammer, in which the attacker hammer both adjacent rows of the victim row, which can trigger a bit flip more effectively. The output of a common rowhammer attack may vary, ranging from data corruption or information leak, or even privilege escalation, depending on where the bit flip happened and how the attacker exploits them. Although the DRAM vendors claim that rowhammer issue has been solved, there's a worrying trend that the technology node size of DRAM keeps decreasing over recent years. On one hand, this will increase the density of the DRAM so that people can get more DRAM with higher capacity or with better cost efficiency. But meanwhile, this also leads to a trend that the minimum access rate needed to rowhammer keep decreasing. And the recent studies show as low as 150K access per second can trigger bit flip in newer DRAM modules. In other words, the DRAM modules are becoming more vulnerable to rowhammer attack. Now, let's get back to our topic. What challenges do we face to rowhammer an SSD? First, the SSD works as a black box. People have little to no knowledge about its internals. Also, the attacker won't be able to run customized rowhammer code directly inside the SSD. To solve the first challenge, we can try to pry open the black box and then reverse engineer its internals. And based on the reverse engineer result, we can try to find an indirect way to launch rowhammer workload inside SSD. So we tried to reverse engineer a popular consumer level Samsung SSD with the model name 850 EVO, as shown in the figure. We learned that this SSD actually works as a computer system itself. For example, it has a 3-core Cortex-R4 ARM CPU and 512 megabytes of LPDDR3 DRAM, and it provides 120 gigabytes of non-flash storage. And then we try to learn how the DRAM on this SSD is being used. The DRAM is used to store the FTL runtime code and data, and it also provides a buffer for incoming I/O command. And also it has a logical to physical mapping table, which is also called L2P table, to translate the logical address, the LBAs, to physical addresses inside the NAND flash. The L2P table is commonly organized as a linear table or hash table. And also we observe that the DRAM accesses inside this SSD is not cached. So we learn about some internals. Can we rowhammer the DRAM inside this SSD? It looks like the L2P table is an interesting spot to start with. Here we take a closer look at the L2P table. We use a linear table layout as an example, which is essentially a linear array indexed by the LBA. When a host read request comes in, the LBA will be used to index into the L2P table to translate into physical block address. Then the corresponding physical block will be read and returned to host. So it looks like we found a solution for the second challenge as well, in which the attacker can make use of normal read requests to trigger accesses to different regions in the L2P table. Based on the observations we have for now, we propose a rowhammer attack on the L2P table. To make it easier to understand, we assume a range of L2P table entries are located across 3 consecutive rows as shown in the figure. And then the attacker sends a sequence of read requests with carefully chosen LBAs so that the corresponding L2P entries alternatively fall into the 2 side rows, just like in the double-sided rowhammer attack. Thus, the middle row, as the victim row, will have bit flip in one of the L2P entries. The bit flip will cause the L2P mapping being redirected from the original physical block to a different one. To justify the possibility of such attack, we note that latest PCIe Gen 4 SSD can provide around 1.5 million IOPS compared to the minimum access rate to trigger bit flip we mentioned earlier, which is as low as 150K access per second. So this is truly raising a red alert to people. Now we have a bit flip inside the SSD DRAM. Should we expect the same outcome as the host side rowhammer attack? First, we expect the data corruption is still the most straightforward outcome. But as for the information leak and privilege escalation, exploit for host side rowhammer attack would not work here. So we need to develop new exploit for SSD rowhammer attack. Here we take information leak attack as an example. We will target the ext4 file system, which is widely used among Linux systems. The ext4 file system supports a legacy direct-indirect block addressing mechanism in which the inode can contain direct pointer to data blocks as well as pointer to indirect block, which itself store pointer to data block. Note that the indirect block is not protected by any checksum, which leaves it easily exploitable. So the attacker can construct the data block to mimic the structure of an indirect block. Normally, this fake indirect block won't cause any damage. Next, we show how we turn it into a data leak attack. Here, the attacker creates a file with an indirect block pointing to a data block mimicking the indirect block, and contains the LBA to a data block C. Note that on SSD, there's an additional layer of indirection where the LBA need to be translated by the L2P table to point to actual physical block. And now, the attacker can launch rowhammer attack on the L2P entry for the original indirect block and cause it to be redirected to the fake indirect block. And thus, the attacker-owned file will now follow this fake indirect block to access data block C, which the attacker originally has no access permission. By this, we turn the bit flip inside SSD DRAM into a data leak attack. In conclusion, we have shown that the threat of Rowhammer attack are extended to a new dimension, the storage devices. But there are still many open problems. For example, can we apply other host-side attack on SSD as well? And as for mitigations, we discussed some possible solutions in the paper, but there's still some unexplored space. And do we have a more principled solution for similar threats instead of doing the attacker and the defense game over and over again? Thank you for listening.